potassium. And we coupled those models with a simple ion transport model to estimate for the first time fluxes of exo-ions from up to 18 lunar ion species. Some of these models are simplistic, just Chamberlain models. Some other models like the helium and sodium ones are more elaborate. And the idea is that ARTEMIS does not resolve pickup ion mass. So the question is, can we use a model of pickup ion transport, having validated something about the neutral measurements, to estimate what types of masses hit the instrument, and in fact try to interpret, go even further, try to interpret relative and absolute, if you wish, exospheric abundance. So the scientific questions that drive this is, again, most of the expected constituents of the lunar exosphere remain undetected. And so the two questions I wanted to ask were, what is the relative importance of the exospheric versus the surface sources of ions? We know from laboratory measurements that when the lunar surface is bombarded by solar wind ions and electrons, you emit ions along with neutrals. The question is, if you have a mix of both, can you uniquely constrain, for example, exospheric ions? Are they important? If the question to the first is yes, then can you go ahead and infer relative abundances for all these undetected neutral ion species based on these measurements? So in a recent set of papers, one appeared in JGR space earlier this year, and one in a GRL appeared about 2 weeks ago. We just developed some model profiles here shown above the subsoil point for all the species that we'll study. Most of them, like for the refractories, we did proper counting, if you wish, of the contributions that solar wind spattering and micrometeoroid impacts can provide. The model of sodium, as Rosemary showed, was validated against measurements to within a factor of 2 about a couple of years ago. The helium model here goes back to the days of the LACE detections by Dick Hartle and Thomas. And for other volatiles such as carbon, sulfur, etc., we don't have appropriate models. We just assume a Chamberlain model at 400 degrees Kelvin and the upper limits from Stern. So the question is, how well do we reproduce the upper models for the refractories? And for sodium and potassium, for example, where detections exist, for sodium, Rosemary showed that we're doing a pretty good job fitting the data curve, but not the details perhaps. The sodium to potassium ratio is consistent with what's measured, roughly a factor of 4. How about the other species? So there's a color-coded here. Blue is supposed to be the solar wind and impacts providing way less than upper present limits suggest. So these are, for example, iron and magnesium. On things green, like oxygen and aluminum, basically present limits from UV measurements break even with what's expected by solar wind and impacts. And then you get into the orange, slightly exceeding present upper limits for titanium and silicon. And we inferred that the lines based on which these limits were inferred were actually largely unpopulated. So these are somewhat suspect and can be revised further. But the clear limit we got here was for calcium. We expected about 40 times more calcium to be present in the exosphere based on the effect of impacts, for example, than the existing limits. So one way to rephrase these results is that the only time where we see a stringent limit for modeling is from the calcium measurements. Everything else is still up for grabs. But we concluded that because of significant uncertainties in the microphysical parameters driving the exosphere, it's very likely that these predicted abundances for the exospheric refractories are already upper limits. So the point is, we now have an exosphere model that pretty much matches what we can expect. We can expect to draw no more ions from this exosphere than what we're putting in here. And we're coupling this with a solution of the Vlasov equation with an ion source term, which we presented last year in a paper with Dick Hartle leaving. And basically what this says is that if the fields are assumed uniform, magnetic and electric fields, and there's no draping all the way down to the surface and little effect of surface charging, and you disregard magnetic anomalies and all that other stuff, which is okay in the day side. Basically, you end up with a particle distribution function that looks like this. It's a one-dimensional, the particles are still in a ring distribution. It's a one-dimensional function of velocity. And basically, this function here relates the probability, if you wish, of a velocity vector arriving at an instrument back to its point of origin. Just the rate, the density model here. So you just grab the density, the exospheric density from our model, and you sum it up over all cycloids, the map from the position of the instrument, say, and that velocity vector back to where it originated. And so, of course, integrating this one-dimensional function, you get macroscopic fluxes, densities, etc., etc. So we put together a simple comparison for Parker spiral IMF, where we plugged in all these exospheric models at essentially upper limits, and we also assumed for the surface ions, just to estimate the relative abundance of the relative importance of the exospheric and surface ion sources. We assumed the yields by Elphick et al. For solar wind sputtering, solar wind induced ion sputtering. And you see that what one finds out is that if you believe those upper limits for species like aluminum and silicon, the expected contribution to measured flux somewhere above 100 kilometers altitude above the moon much exceeds what you expect from the surface. Now again, I said this may very well be just upper limits, but for things like sodium, whose exosphere is well described, as I said, within a factor of 2. See, again, we expect about 10 times more contribution by the exospheric term than from the surface one. For other species such as calcium, titanium, iron, we found that those are primarily driven by surface source rates. So armed with these expectations, we can go back and look at some of the measurements that Jasper presented. And if you compare to some of the previous measurements by Wind and Kaguya, there are some discrepancies. For example, we can't explain why there's so much O+ been recorded by these instruments. One idea is that it's molecular ions breaking inside the instrument. And if that's so, ARTEMIS is not going to return a lot of oxygen because it doesn't have a foil. Also, there are some other discrepancies, but notice that even within measurements there are discrepancies. For example, Wind doesn't record any potassium plus, but potassium plus appears to be prominent in the Kaguya measurements. Now, in the GRL, I spent a lot of time showing why relative abundance, inferring relative abundance from Kaguya measurements, which has a finite field of view. You have to do this very carefully. There's a lot of biasing because some species may not be mapping efficiently into the instrument because of pointing. So at least we have a handle on this. So the question is, what can we expect for ARTEMIS? So if we average all over those events that Jasper showed, I added those 18 species in the model, most of them at upper limits. And again, you should expect to see a lot of aluminum and silicon, prominent sodium. And so this indeed looks like the laser pointer is dying. It does look like you should expect at least some peaks around 24 and 39 or 40. And the only comment I have to make here is that these are omnidirectional flux estimates versus the estimates that the inference that Jasper made was based on the peak channel. So this is though what's actually measured. And what I did here is simulate the energy spectra that the instrument would see based on the expected neutral levels. This is just the exospheric source for the time being. And what you see is here in dotted blue, I've just added helium, oxygen, sodium, and potassium to the mix. This dotted blue is the energy channel at which ARTEMIS detected the peak flux. And you see that consistently throughout this series of events. It's matching to where an exospheric source would give you a peak. So this is well consistent with an exospheric source for the most part. See that often helium doesn't match into the instrument. You see that it has picked up twice the solar wind speed that it's allowed to. and it's not included in the, it doesn't get into that channel effectively. You can accelerate it. But on occasion, you do. Most importantly, oxygen is always in the mix. I mean, we should be recording oxygen and gets into the instrument if it's there. I also added separately in crosses there the surface ions, the energy channel with surface ions would match to. And you see that in many occasions, you know, there are one channel or maybe two off. Sometimes we see them right at the where the instrument recorded them. So they should be playing a role, but I think mostly we're seeing exospheric ions here. So what is the concept here? Is just to use the you know, this mastics corresponding to unit exospheric density and use them in an optimization scheme. ARTEMIS provides this differential flux at the peak. Formulate this as a penalized least squares problem, and the penalization here penalize the sum of the relative abundances, if you wish. It's meant to stabilize the regression to collinearity between different species. I mean, if you have you know, both methane plus and oxygen plus and N plus, for example, they're highly collinear. I mean, they vary from measurement to measurement. So the way we do this, you first have to estimate how much of this bias to apply, and that's done with cross-validation, where you partition your data set in say, 10 folds here, and you iterate 90% of the measurements. You use it as a test set or train set, the rest of the 10% as a test set. You estimate the prediction error as an average over all iterations. And what you find here is that there's a lot of ways to fit this data. Basically, it's what it says. And this is, for example, the solution path, relative abundance for all these species as a function of how much bias to apply. And you see that several of these coefficients just drop out of the mix, like magnesium, CH4 plus, C plus, they're just not important. You see that things like silicon, sodium there are in the mix, helium is in the mix, surprisingly N plus is in the mix. So since all these solutions are effectively equivalent, what I take to be the most likely solution is the one that gives you the right expected helium to sodium ratio, which is somewhere around here. So this is the punchline. This is what we predicted we might expect to get, and this is what we infer if we scale the sodium stick, you know, to match the expectation. So what do you see here? The sum really of aluminum and silicon is, compared to sodium, is where it should be expected to be. We don't see any oxygen. Instead, it's picking up some volatile, really the sum of CH4 and N plus as a possibility in this mix. So basically, it doesn't like cold oxygen. It likes a cool something at that mass. It could also be neon. I don't have all the species in the mix. What's rather surprising is that all these elements, calcium, CO2, iron, they're relative to sodium much higher than expected. This is really telling us that effectively we have some missing elements from the mix, perhaps argon plus. I mean, basically, if I put limits to this, we would consistently underestimate the measurement without extra species. You see here how we called out the surface abundance separately, and you see that it's always in the mix, but mostly we're seeing exospheric ions. So just to conclude, we're using the model as the ion mass spectrometer here, and proven regression techniques that promise to constrain the relative abundance of exo ions and surface emission rates from ARTEMIS data. Just based on the peak detection channel, energy channel, most detections are consistent with exospheric source. You see how well they match to what's expected from the exosphere. Relative abundance of sodium to aluminum plus silicon plus expected from models. Some surprising results and slightly unrealistic, suggestive of some missing, species in the mix. And we're performing some sensitivity analysis now, and also we're using the full spectrum detected by ARTEMIS on each of these events, which should help constrain the results greatly. Thank you.